Okay, so let's go.
Thank you. So Laurent and I are going to present to you this long study that we've done for the ADEME. The project was a very long project. It lasted like 26 months total. The idea was for the government, so French government and the ADEME, to launch a study on how digital solutions are helping other sectors to lower their environmental impacts, and to what level the digital technologies did contribute to the decarbonizations of the other sectors, and at which level it managed to lower the environmental impacts as well at the level of the state. So it's the first time a state launched this type of study, and we studied different use cases, 9 of them, and so it's one of them that we are going to present today. But the 9 case studies that can be found on the ADEME library are one about agriculture, like nitrogen fertilizer application, some of them in the energy production sectors with the control of high voltage power lines, and applications around monitoring solar panels for residential buildings. In transportation and mobility, we had tire management, teleworking and carpooling platforms. And the last sector was city management, and it's one of them that we are going to present today with street lighting. And Laurent and I did another one around identification of water leaks in water networks. And the last one was around building management systems. So very various topics. The idea was to study digital contribution in those sectors. And so the selection was firstly done on solutions that tend to have a benefit in terms of environmental impacts. So that's it. And maybe what we can say, because we agreed with Laurent, is that if you have questions, don't hesitate to ask the questions directly in the presentation. We are not that many people today, so if it can be interactive, it can be good as well. So in public lighting, sorry, same mistake. We worked with many different people. So, of course, Laurent and I are experts in assessing the environmental impacts, and not especially in public lighting, and not at all in all the different use cases that we had to study for the big wider project. So we had to have around the table many different people, manufacturers, experts, generic experts, local authorities. So here it was mainly different cities that deployed new systems in street lighting. And as well, we had a critical review to go through all the study and review all the calculations that we did for computing the impacts. And just before, the consortium that was built for the project was made of Mavana. So I'm working at Mavana, from Hublot, where Laurent is working, and from Desdemain. So 3 different companies and many experts around the table to drive the study till the end. So quickly, reminder in terms of methodology that we've used for the study. So we've used a consequential life cycle assessment approach. So it's quite different from what we usually use, which is attributional life cycle assessment. In a attributional life cycle assessment, you're looking at the system and looking at how much of this system you need to attribute to your digital solution. In a consequential life cycle analysis, you look at the system, you're going to deploy a new solution. So we can see here on top the deployment of the solution. And you're going to evaluate the impacts of the deployment of the solution as well of the effects this solution is going to bring on your system. So here, if we look at public lighting, for example, of course, you need to assess the deployment of the solution, but you're going to assess as well whether it's going to reduce the travels from technicians, whether it's going to reduce, for example, the consumptions of the your lighting systems, and all the different impacts, indirect impact that the deployment of this digital solution is going to bring on your system. So that's really the consequential approach. And it's an approach that it's more appropriate when you're looking at the system on the long term and how your system is going to be modified by the deployment of your digital solution. And usually what we, and it's not usually, it's when we are looking at a consequential approach, we are comparing the deployment of the solution with a reference scenario. And it's very important to pick your reference scenario correctly, because if you're too pessimistic or too optimistic, the assessment that is comparing your solution with the reference scenario can be as well estimated or overestimated. And so you need to assess as well how your reference scenario is going to evolve in time, how your digital scenario is going to evolve in time, and you're comparing the two scenarios, and this is what you're going to quantify.
Is it okay with everyone until that point? Yes, it is. So you can continue, Fabienne.
Okay. So now I'm going to deep dive more into the public lighting solutions. Yeah, so in this specific study about public lighting, what we've modelized is really a reference scenario without digital technology. Digital solution that we call simple solution that is without connectivity, but is still a simple digital solution, and a more complex digital solution that is connected solution, and that is more what you think when you refer as smart city solutions. The angle that we wanted to take is how much a digital solution or a complex digital solution is bringing in terms or is contributing to the transition compared to a more simple solution, and whether a complex solution has more benefits in terms of environmental impacts and compared to a more simple solution. So this is really the approach we wanted to have. So this is why we have one reference scenario and two different digital scenarios. And we've looked at the public lighting systems of a city during 13 years. So that was the order from the ADEME to look at how it's going to evolve until 2035. And Laurent, can we switch to next slide, please? Yeah, and what we've taken, so we've taken a fictitious city, meaning that we didn't want to look at what is going to happen into one specific city, but we looked at a fictitious city, that medium-sized city, we would say, and for all the parameters of the city, as far as much as possible, we tried to use the mean values for France. And in France, the mean value for the lighting fleet is 38% LEDs. So meaning that part of the city has already transitioned to LEDs, and we wanted, and the city was going to replace their old lighting systems, which is sodium bulbs, by LEDs, and this is not what we wanted to quantify, but the digital solution was deployed meantime as the renewal rate, so meantime as the city was transitioning their sodium bulbs to LEDs lights. So the 38% of LEDs that was the starting point, and every year the city was replacing 3% of their old light bulbs with LEDs, and at the meantime was switching to a digital technology to automate part of the operations. So of course we didn't want to quantify the switch to LEDs in the digital benefits, so that's out of the scope. And we've used as well French electricity mix. So you need to be very careful with that, because in France we've got a very specific electricity mix, and so the results of the study cannot be extrapolated to other countries without complete recalculation of some of the effects. And as well, so not only French electricity mix has been used, but we've projected as well the evolution of the French electricity mix till 2035. And another parameters that we've made evolve in time is the engine mix of the cars used by the technicians to visit the lights in the city. So when car needed to be involved, the energy mix of those cars was evolving in time as well. So reference scenario. So we've got a figure over there that is explaining what was the reference scenario. So in this reference scenario, we had a cabinet that you can see here on the right. And this cabinet was including astronomical clocks. And those astronomical clocks are triggering the on and off of the lights for all the city. So basically, the astronomical clocks were switching off the lights at the sunset and switching off the lights at dawn. So that's how the reference scenario was working. We kept 100% lighting all over the night, so no nighttime switch off, but the nighttime switch off has been evaluated in a sensitivity analysis, and we had involved as well event management. So event management is, for example, when you need specific lighting profile, because, for example, you've got a fireworks event during the summer, and you need to switch off the light during the fireworks because otherwise people don't
Excusez-moi, je
see
suis
the
en réunion
fireworks.
là, mais je connais bien Action contre la.
Okay. And in terms of operations and technicians moves, so technicians had to go on site to install the solution. There were as well fault detection, so the technicians had to do some nighttime rounds to see whether the lights were working correctly or not. So that's a usual process in street lighting when there's no remote possibilities to do it. Regular updates and even related updates. So regular updates is, for example, to do a software upgrade from the astronomical clock in the cabinet. And even related updates is for technicians to go in the cabinet to trigger the switch off or switch on of lights for specific events. And then replacements of faulty equipment. When something wrong happens, you've got to send your technicians to repair the lights or the drivers or the cards in the cabinet. So that's reference scenario. So now the simple dimming solution that we refer as SDS or SAS. SAS is the French acronym. So in that case, we still rely on an astronomical clock in the cabinet, but this time the astronomical clock has the possibility to send commands to the light bulbs through a driver to dim the lights. So dimming the lights, meaning that in terms of profiles, you have the capability to send commands to say the lights need to be configured to only 50% of the maximum lighting possibility. So that's what you see on the scheme in the middle. So in our quantifications, we've modeled only 2 levels of powers, full power or 50%. And that's following the recommendation of the European Commission. So that's minimum recommendations. So that's, I would say, minimum lighting, minimum dimming profile. So same here, we had some operations for technicians to go on site. You still have nighttime rounds and replacement of faulty equipments. And then if we look into the more complex solutions, so here we have more components in the cabinets. We have what we call management control system in the cabinet, and this management control systems is sending commands directly to the drivers using LoRa point-to-point solutions, and is sending as well levels or results of what's happening on the field to applications, to some applications, specific application systems as well, that are gathering all those data and that provide as well the possibility to command directly the systems from the internet. And this is done using LTE-M solutions, so based on cellular solutions, and are providing capabilities to the technicians to command directly the lights from remote. And so here, in terms of profile, we have modeled the same type of profiles, but you have possibility to trigger the dimming at any point of time in the night. Event management, so you're able as well to switch off and switch on the light directly from remote without sending a technician on site. So with this type of solution, you're lowering much more the need to send technicians in the field to either identify that lights are not working because you have the information automatically, or as well to send the technicians to be able to switch on, switch off the lights for specific events. So key assumptions for the study: fleet growth rate. So we assume a stable fleet, so a stable number of lights in the town. Electricity mix, I introduced you already to that. So we use the linear trend based on ADEM. So the electricity mix has been modeled to evolve in time. Engine type has been evolving as well till 2035. Type of communication. So we assume that the LTEM solutions will still be able to work in 2035 without being replaced. So this has been validated as well with the scientific and technical committee. And average rated power of the LEDs, we've modeled as well of the fact that every year the LEDs that we were deploying in the field had lower consumption. So every year the LEDs were better and better, and so the consumptions from those LEDs were reducing over time because the new LEDs were consuming less than the older LEDs that were deployed in the beginning of this study.
Okay, maybe we can have a small pause right now to take some questions or comments, because I believe that the study is quite heavy. Are there any questions? Nope, no question. Okay, so I'm gonna, Fabienne, we switch on that point.
Yeah,
I'm gonna talk a little bit about the consequence trees. So the consequence trees is a tool that we use to understand the consequences of deploying a connected lighting solution when you compare it to the reference scenario. So for building those consequence trees, we had workshops with all the stakeholders in the projects, and we asked them to what were the consequences that they were seeing when deploying that kind of solution. And so we tried to document that and to map those consequences. So on that slide, you've got consequences only for the direct effects, which are related mainly to deploying the solution. So one effect is the deployment and usage of digital equipment on the lighting network, and you see on the red bubble the negative impacts related to that effect. So when you deploy and use new digital equipments, you've got an impact which is related to those equipments, the life cycle. So that's on the simple and connected scenarios, you've got those impacts, but on the connected scenario, you've got added effects and added impacts. For instance, on the connected scenario, the solution is going to use the LTEM and fixed network. So we'll have to add the negative impacts of those networks usage. On the connected scenario, you also have to deploy data center equipments and software on those data center equipments. And so for that, you'll have the impact, the added negative impacts of the virtual machines that you're going to use for the software. Also, on the connected scenario, you have increased response time, and so you have an increased impact of the technicians for the round trips. And you have also increased failures related to additional electronic devices. As you add more electronic devices, there are more chances that those devices will have a failure. So you have, again, increased impacts of technicians to fix those devices. So these are the impact for direct effects, but also there are indirect effects. And so these are just a sample of the indirect effects that, these are just a few samples. And then on the next slide, you'll see all the indirect effects that we have documented. So when you deploy the connected solution, for the connected scenario, you don't have to deploy an astronomical clock. So we can avoid deploying that one. And so we can reduce the impacts compared to the reference scenario regarding that astronomical clock. And on the simple scenario, if we deploy a connected lighting solution, a digital lighting solution, the light intensity will vary compared to the reference scenario. So we can optimize light pollution, we can optimize energy consumptions, and both those effects can reduce the impact on biodiversity and human health, and also reduce the impacts regarding the energy impact, the energy which is not consumed actually. So these are all the effects that we identified and quantified. So basically, we identified lots of effects and we quantified each effect one by one, and then we summed all the positive or negative impact of each effect. So on the direct or first order side, I already talked about it, but we quantified the deployment and use of digital equipments on the Lightning Network. We also identified the impacts of the increased intervention time. Basically installing a digital solution takes more time than installing a simpler solution. So the technicians make more run trips to the light points. There were also the use of the digital network, which is the data exchange of LTEM and internet. There is also the deployment of the software in the data centers. These second order effects or indirect effects were additional failures of digital devices, avoidance of deploying and using an astronomical clock, the modulation of light intensity over time, remote control provided by the connected solution, and the fact that people in offices could trigger the lightning on off or the level of the lightning that they wanted. And also, the last second order effect was the reporting of the installation status. The technician didn't have to go in front of the lightning to know that things were okay. This the status was reported directly to the people in the office through the internet. And then there were higher order indirect effects or rebound effect risks, which were rebound effect related to financial savings. This one is quite tricky because this was about when you can better manage the lighting level of your light network. Basically, you save money on electricity, but this money that you've saved on electricity, the city can decide to reinvest it in other activities, which can be low impact or high impact activities. I mean, environmental high impact or environmental low impact. And if the city decide with those money saving to reinvest it in high impact activities, this can negatively impact the net balance of the solution. And another higher order indirect effect or rebound effect of the deploying connected lighting solution is basically as you set up internet connections to your lighting poles in the street, you can add more digital solutions on that poles. For instance, you can deploy cameras to let's say security cameras. You can deploy atmospheric pollutions sensor. You can deploy lots of other solutions which can again negatively or positively impacts the net impact of your solution. Yeah, so those were all the effects that we quantified. If you want to ask question, feel free to do so right now, or we move on to the results. So concerning the results, so this slide is just to give you an overview of the impacts by tier of the deployment of the solution, of the direct effect. On the simple dimming solution, there were no additional equipment which needed to be deployed compared to the reference scenario, so that there were no direct effects. But for the connected digital solution, there were additional street equipments, and there were also data center and cloud software. There were also additional human operations, which were basically the technicians who moved on site to install the equipment. So those were all the impacts, and you can see that the most impactful tier is the street and user equipment, the equipments that we had to set up at the just under the lighting pole. So yeah, tier 1 is by far the most significant. So those were IoT and sensors for each light point. And yeah, so yeah, we had a lot of IoT, so those impacts were quite heavy. So those were for the direct effects, but now I'm going to share with you the results for net impacts, where we aggregated both direct and indirect and higher order impacts. And I'm sorry, those graphs are quite small, but I hope that you can read them. Just for your information, on the left side we have the results for the simple dimming solution scenario, and on the right side we have the results for the connected digital solution. So you can see that and also on the graph, you can see the green bars are presented to explain that one specific effect is providing benefits, reducing the impact of the solution, and the red bars are indicating negative effects where we have added environmental impacts. And you see on the bottom of the graph, you see all the effects. We've got direct effects, astronomical clock, deployment avoidance, time varying light intensity, remote control, system status feedback, and the green bars are for sums when we sum both the negative impacts and the positive impacts. And so you see that on the simple dimming scenario, we've got one green bar which is related to the time varying light intensity effect. So basically, when for this scenario, as we have a different dimming profile than for the one for the reference scenario, we can save a lot of electricity. And so by saving that electricity, we can reduce the impacts on that criterion. I forgot to say that this slide is specifically presenting results on one criterion, which is research use for fossils, ADPF. And so on the simple dimming scenario, we got environmental gains thanks to modulation and dimming, which is around 14.5 terajoules per city, which is around 2,200 barrels of oil, which is not extracted thanks to that solution. And on the right side of that screen, you can see the results for the connected digital scenario. So here you can see a big green bar again for time varying light intensity, because we also have a better dimming profile than for the reference scenario. But you can see also there is a small red bar going up, which is related to the negative impacts of the equipment that we have to deploy on the light pole. And also we have, let's say, a risk related to the impacts related to new telecom networks that you can build on that connected solution with that connected network. So to sum up, we've got environmental gains mainly thanks to modulation and dimming of the light, but we've got environmental costs due to the equipment deployed for the solution and to potential rebound effects. So still we have gains here for that scenario. So something like 12.8 terajoules for the city, which is around 1,900 barrels of oil not extracted. This slide is looking at another environmental criterion, which is resource use, minerals and metals, ADPE. Basically, for the SDS, we have really minor environmental gains related to dimming, and so I'm not gonna talk more about that scenario. But for the connected digital solution scenario, you can see that big red bar, which represent negative impacts on that criterion. And so there are significant environmental costs related to IoT equipments which are deployed in the streets on the poles of the street lighting. And we've got minor environmental gains related to dimming. You see those really small green bars. And we've got limited indirect risk related to induction effects, which are the impacts of equipments that you deploy if you deploy new telecom networks and you equipments related to smart city solutions like camera and let's say atmospheric pollution sensor and so on and so on. And so for that connected digital solution scenario, the net impact for that criterion resource use minerals in method is plus 3.7 kilograms of antimoine equivalent per city, and it's the equivalent of manufacturing and using something like 1,400 smartphones. So it's a negative impact. So basically, deploying the connected digital solution scenario is bad from an environmental standpoint on that criterion, where it was good on the previous criterion. Next criterion that we look at is the climate change, which is a little bit more complicated. And again, if you get questions, please stop me and ask me your questions. So if we look at the simple dimming solution scenario, you can see that we've got, again, a big green bar that we have in many graphs, which is related to the benefits that we have because the light intensity is reduced globally on that scenario. So we've got environmental gains thanks to modulation and dimming, but we've got environmental costs related to rebound effects potentially linked to financial savings. So that's what I talked about earlier. If you get economical savings regarding the electricity that you don't use, the city can decide to reinvest that money in potentially bad and impactful services or solution, and that's what we wanted to show on that graph. And I didn't tell it, but when we have let's say lined red graph, it's not that the effect will automatically happen, but it's a risk that the city must consider and must monitor and must mitigate. So overall, on the simple dimming scenario, we estimated that we still have a gain, which is something like 45 tons of CO2 equivalent per city, which is the equivalent of the footprint of 5 French people. On the right side, you can see a graph which is quite different. And first I want to attract your attention on the 0 point. You can see that the 0 point on the graph on the left is at the top of the graph, while on the graph at the right, the 0 point is let's say 1/3 below the top of the graph. So it's not you can't directly compare the two graphs just graphically. So on the graph on the right side for the connected digital solution scenario, you've got still a green bar which is related to gains related to the energy saved by dimming the light. You've got also savings related to remote control. You've got saving, but very small savings related to system status feedback, which is provided directly to people in offices without needing people moving on the light point. But you also have a red bar related to the direct effect, which is mainly the impacts related to IoT equipment deployed on the lighting. And again, you also have rebound effects related to the reinvestment of financial gains, and rebound effects related to potential new new IoT solutions deployed for camera, security cameras, or other type of IoT and smart city solutions deployed. So to summarize, we've got environmental costs related to the deployment of IoT equipment. We've got environmental gains, which are fairly close to the SDS scenario, especially time varying light intensity. And we've got significant indirect risk related to the use of savings, related to the use of financial savings, and to the induction effects related to smart city solutions, which can tip the cost-benefit balance. That means that depending on how you reinvest your money, or depending on whether or not you deploy smart city services on top of your internet connections, you can have either environmental benefits or environmental costs on that criterion. And so for that specific configuration, we estimated that we had an environmental cost which was plus 43 tons of CO2 equivalent per city. But again, it depends on the exact parameter used for that model. And so those were the results for the main criterions that we looked at, but we also performed some added sensitivity analysis. And well, I'm not gonna go through all the sensitivity analysis, but maybe, yeah, we had a sensitivity analysis related to the power of the LED modules, because we modeled the result with a 60 watt LED module, but we know that there are other LED modules which have less consumptions, and so we performed the sensitivity analysis also with a LED module of 30 watts. We also had other sensitivity analysis with other lighting dimming profiles, because we know that some cities deploy very aggressive lighting profiles where at some point the light is close to zero. And also we had a sensitivity analysis with different solutions where we have a different kind of equipment on the light point. And yeah, so those are examples of some light dimming profiles that we tested. And well, yeah, this is some results about the dimming profile, and I'm not going to go through all the explanation, but we saw that the dimming profile adds a very can change the results, and that the aggressive profile is one that generate the largest gain overall. And so these are the main results, and I'm going to go through the key takeaway, which are the main conclusion of this study. And so, yeah, the first conclusion is digitalizing the public lighting does not systematically guarantee environmental gains across all the criteria we analyze. We saw that the simplest solution, which was not connected, was the solution that provided gains of all the four main indicators that we studied. And we had a significant benefit on ADPF, which is fossil resource depletion. And this was mainly due to the use of nuclear power on the French electricity mix. The connected solution had more mixed results. It was the more advanced solution, but yeah, basically we had environmental cost on ADP and GWP, and minerals and metals and greenhouse gas emissions. So we had negative costs, negative impacts, and we had gains, so benefit impacts on ADPF. But also we saw that if you account for higher order risks or higher indirect effects, well, those effects can tip the results and can basically make the solution either providing benefits or providing costs, depending on the way you reinvest your money or the way you leverage the network that you deployed. So the city has to be really mindful of those effects. So the cost benefit balance depends of the solution depends on technical and policy choices. The net environmental results of deploying a solution is highly sensitive on the type of lighting profile as well as the technology of the selected solution. And yeah, from an environmental standpoint, switching to the LED technology and choosing the most energy efficient LED modules is the main lever for gains to consider before digitalization. So for city, thinking about either deploying LEDs or digitaling the light network, the first thing to do is to deploy LEDs and then think about which kind of digital solution can help improve the gains provided by the LED lighting. We had also a little calculation about how that solution can help with the French low carbon strategy, and we showed that those solutions don't really help the French low carbon strategy. It's quite marginal regarding this topic. And that's it. That's all we wanted to share with you. I hope it was clear enough. I believe it's a quite complex study. Also, maybe presenting it in English is not easing the understanding of the study, but you can ask questions right now to Fabienne and I. And if you want some more information about this study and all the other ones that we've provided during these 2.5 years, you can have a look in the ADEM library. I'm sorry for the people who speak English. I think I'm not sure there is a translation in English of any of those cases. And I believe that this presentation is the first one that we perform in English. Yeah. So that's it.
But we can answer to questions about other cases or explain other cases in case you're interested. Just something that need to be emphasized again is especially on this case and the way that the effect dimming of lights is very dependent on the French electricity mix, and the fact that the French electricity mix is low carbon is resulting into this effect being the largest one, but still with other electricity mixed from countries where it's more carbon intensive, it would have a bigger impact. So we really need to be careful with the results, because first it's a fictitious city, so it cannot be extrapolated to any type of city. Second, it's really a French study using the French electricity mix that is very specific. But anyway, if anyone is interested, we can reproduce with another country's mix if needed as well.
Are there any comments or questions about this presentation and the study? No question. Maybe I'm gonna just put my Boavizta hat again and just say that this kind of study with net impacts is quite new. We don't see a lot of studies like that often, and I believe it would be really cool if people within Boavizta try to appropriate themselves those kind of things and launch discussions so that we have more thinking about net impacts within Boavizta. Because until now, within Boavizta, we had lots of studies and work on direct impacts, and it would be cool to have more on indirect impacts.
One question, maybe, Fabienne and Laurent. I remember the methodology started by Shift Project and then broadcasted worldwide with WBCSD, something like that, of émissions évitées, avoided emissions. That is reminding me of that because I used it at some point. You had to define the reference scenario, and then is it building on that, but just putting more emphasis or on indirect effects, or are there big differences, or is it totally different initiative?
I don't remember the methodology used by the Shift project, but I think it may be quite similar. I don't know, Fabienne, if you get any answer about that.
So my answer will be more general and not specifically compared to the methodology of the Shift project. But if you're looking at the case we've presented, avoided emissions for me would really be the emissions avoided by dimming. So it would be one effect. And usually companies, when they talk about their avoided emissions, it would be limited to that. So, okay, my solution is made to be able to provide dimming functionality. This is what permits the dimming functionality in terms of avoided emissions. Still, that's not enough. And what we've been looking at is the effects on transportation, like the trips done by technicians, which is usually not taken into account into avoided emissions. And other effects as well. And we've really wanted to focus on, as well, on rebound effects, which are never looked into. And those rebound effects are risks that need to be taken into account and mitigated as much as possible. And the type of methodology that we've worked on permits to identify those rebound effects. And this is really done by building the consequence tree with actors that comes, and not only the provider of the solutions, but the customer, that is, like in our case, the city, how the city is going to use the solution, how the technicians' job are going to be altered by the solutions, and as well, what are the other effects beyond the solution that the solution is going to bring.
Okay.
And having as many actors as possible on the table when building the consequence trees is really key, because otherwise, if you only have, for example, the solution provider, you will only focus on the avoided emissions. And that's not the point of the methodology.
Thank you, that's helpful.
Thank you, Fabienne, for giving a better answer than myself.